Today's demo is about how to simulate a PROFINET network with SpeedGoat hardware in order to test a programmable logic controller. My name is Alexander Beck. I'm Industry Manager at SpeedGoat for Industrial Automation and Machinery. Programmable logic controllers, PLC, are industrial computers controlling multiple applications in industrial plants. For example, wind tracking in wind turbines, lighting in tunnels, or cutting paper in a newspaper printing machine. On the one side, the PLC receives working instructions from higher-level supervisory control stations. On the other side, the PLC communicates to devices on the field level, such as sensors, motor controllers, and robots via industrial protocols. In the present case, it's PROFINET. Testing a PLC is challenging because it requires the PLC to be connected to the real plant. Ahead of the final on-site commissioning of a plant, hardware-in-the-loop simulation allows to test the PLC application in the lab. This is done by simulating the remaining network components such as sensors, actuators, and motor controllers. Such tests are reproducible, adaptable, and can be performed automatically. You can even test the plant operation in edge cases. As a result, hill testing of industrial plant controls is extremely valuable and can be applied to many industries such as manufacturing, tunneling, ship automation, or electric power industry. The only hardware required is a SpeedGoat real-time target machine performing the digital twin of the real plant. I/O modules emulate all connections to plant devices, from digital input-output to Ethernet-based industrial protocols. You use MATLAB and Simulink for model-based development of the plant simulation, and follow the Simulink Real-Time workflow to deploy your application to the target machine. Furthermore, you can interact with the real-time application directly from Simulink for the purpose of error injection, test execution, and signal monitoring. Such a setup enables you to analyze and debug your PLC code and further optimize control algorithms. SpeedGoat offers machines of different performance classes and form factors. Simulation of small units with simple logic is possible as well as large plants with complex dynamics. The key feature of SpeedGoat's mobile real-time target machine is the capability to simulate a high number of industrial protocol interface nodes such as PROFINET devices or Profibus slaves. This machine can take up the multi-node I/O module, allowing physical simulation of a high number of real-time capable slave nodes. Customers can achieve authentic network timing as the module has independent network transceiver for each node. Ethernet-based protocols such as Modbus TCP and PROFINET are supported, as well as serial protocols like Profibus. For the simulation of small plants or subsystems, users can also plug single-node I/O modules into other SpeedGoat real-time target machines, such as the Performance, the Baseline, or the Unit machine. All modules are fully compatible with the Simulink real-time workflow. Each module comes along with a comprehensive driver block set for Simulink and extensive help documentation. The look and feel of the blocks is very much the same along the different protocols. You use the setup block to configure the protocol stack of the I/O module. You use send and receive blocks in order to exchange data with the I/O memory, which the protocol stack shares. This example is about a drive simulation, where the real-time application receives new setpoint data from the network master, performs the drive algorithms, and finally sends back new actual values. Today's demo setup looks like this. I'll switch to my camera right away, showing the live setup, but let me give a brief overview of the setup first. We will see a Siemens PLC communicating via PROFINET. On the one side with a motor controller for motion control and with an I/O coupler. This is for reading switch states and flashing some lights on this simple control box. I will show how easy you can make the SpeedGoat real-time target machine emulating the PROFINET interfaces of both devices. I will also highlight how to configure the Simulink model and finally how to interact with the target and how to monitor signals. Let's go into action. On my desk you see the same gadgets that I have introduced in the last slide. The multi-node simulator, the PLC, the I/O coupler, the switch box, and finally the drive controlling two motors. In a factory, the blue motor could drive a conveyor belt, for example, transporting bottles, and the red one moving a filling needle, filling the bottles. On the control box, there's one switch for operation, one switch for indicating load tank level, and another switch for indicating an open security door. Finally, a knob and the related analog input signal that the PLC receives enables us to slow down or speed up the operation. Filling the tank, closing the door, switching on the plant, makes the wheels turning. All devices are connected via PROFINET. The PLC is the PROFINET controller, and the remaining network are PROFINET devices. This simple network switch here allows me connecting the PLC either to the real PROFINET network or to the virtual and simulated network. In the virtual network, where the drive and the switch box are simulated by the SpeedGoat machine. Before stepping into plant simulation, let us briefly touch on the PLC and how it is configured. The PLC establishes the PROFINET communication to the plant devices and performs the application controlling them. The present PLC was programmed using the Siemens engineering tool TAI. We see some code running on there, some global variables pointing to PROFINET input and output signals, and finally the PROFINET configuration. In addition to the I/O coupler and the Dynamics drive, the PLC is configured to communicate to even more PROFINET devices from known vendors such as ABB, Phoenix Contact, Beckhoff, Schneider and Vago. Those are not connected and thus marked offline in that list. In a final on-site commissioning, the commissioning engineers check whether the two motors stop turning when the tank gets empty. They also check whether the system can be recovered by filling the tank and enabling operation again. And they test whether the plant operates correctly at different speeds. This process is error-prone and time-consuming. How can you do better? Just simulate the network and test your PLC in the lab or on your desk. For that purpose, I disconnect the PLC from the real network and connect to the SpeedGoat machine, and I want this machine to simulate the plant. My Simulink model consists of one subsystem handling the PROFINET communication, another subsystem performs the algorithms for slave device behavior and for environmental conditions. As the demo's main focus is on connectivity, the control subsystem is very simple. You might have a more complex environment, of course. MathWorks provides functions and blocks such as stateflow and SimScape, which help you designing logics and dynamics. So let's move to communication and check the subsystem for the drive in detail. We see the setup block, setting up the protocol stack, the send and receive blocks exchange data with the master. This whole part, including the frame packing, doesn't need to be implemented manually. We provide a MATLAB function doing this job automatically. Let me show you. First, export the PROFINET configuration from TIA into an automation ML file. Afterwards, import the file into MATLAB by calling a speedgoat command which comes along with our block set. The function creates a temporary model including multiple subsystems, one subsystem for each slave. Such a subsystem completely configures the protocol stacks of one node of the multi-node module. It also provides the signals which have been defined in the PLC project. So you automatically get the opposite interface to the variables defined in the PLC. Now you can drag and drop the subsystems to your plant simulation model and connect to input and output signals. Let's download and execute the model. You can do that right from Simulink without the need of additional tools. So now the model is running. We move to the control subsystem. Dashboard controls are available that allow interaction with the real-time application directly from the Simulink canvas. After closing the door, filling the tank, and enabling operation, the virtual wheels are turning. The Simulation Data Inspector, SDI, helps to check for correct operation. It monitors all signals selected for logging. I've checked the commanded speeds for both wheels that the simulation is receiving from the PLC. They are painted black. And I've checked the computed speeds of both wheels that the simulation is sending back to the PLC. Red for the red wheel, blue for the blue wheel. In the model, I designed a simple PT2 element to create this overshooting curve. We can check this on the master side as well. Let's switch to the TIA. As you can see, the PLC feels happy. The drive and the I/O coupler are up and running. In addition, the Simulink model is even simulating the rest of the network. They are all green now. The PLC is communicating to the virtual plant the same way as in the real world. Let's check. Using this trace function. The received speed signals from the virtual drive can be monitored on the PLC side as well. The signals that you see here are the actual speed values received via PROFINET from the real-time target machine. They represent the red and the blue wheel. Back to simulation. If you want to interact with the target machine without using Simulink, you can create a graphical user interface with the App Designer. The App Designer has two views, one for the graphical design and one for the implementation of logic. After compiling, you can copy the final app to any other computer. The user interface allows me to download and start the real-time application. It further allows doing the same actions on the control box as in the physical control box. Closing the door, filling the tank, switching on the plant. I can monitor speed signals, both commanded and actual ones. I can switch between different drive dynamics, from second order lag to first order lag to no lag and back to second order lag. Furthermore, with the help of these controls at the bottom, I can shut down the communication of the simulated I/O coupler and the simulated drive. This allows me to test the PLC reaction on devices getting lost. Let's go back to TIA and check there. As you can see here in the device list, both stations are offline. I hope you enjoyed this introduction to hill simulation and testing. I'd like to encourage you to take advantage of model-based design. Transform your plant into a digital twin using Simulink. Follow the Simulink real-time workflow, perform plant simulation models in real time on Speedgoat hardware. Emulate industrial protocol interfaces with our field-proven I/O modules. Test your plant controls already in the lab. Explore the integrated instrumentation and interact with the target machine directly in MATLAB and Simulink. That's all for today's demonstration. I'm looking forward to guide you through the test automation workflow with MATLAB and Simulink test in an upcoming demonstration. So stay tuned, thanks a lot.
You want to learn more about real-time controls testing? Then find additional content linked here.